Good afternoon. We have the pleasure to welcome today Professor Athanassios Z. He is currently the Susan Dod Brown Professor and the Department Chair of the Department of Chemical and Biological Engineering of Princeton University. His research group focuses on the development and application of theoretical and computer simulation techniques for the study of properties in fluids and materials. Their emphasis is on molecular-based models that explicitly represent the main interactions among microscopic constituents of systems. Among his research interests, we can highlight polymers under non-equilibrium conditions, self-assembling of nanoparticles, and properties and models for electrolyte systems. He has received numerous awards and honors, including the American Institute of Chemical Engineers Coleman Award and the President's Award in Applied Chemical Thermodynamics. He was elected to the U.S. National Academy of Engineering in 2004 as a fellow to both the American Academy of Arts and Science and the American Association of the Advancement of Science in 2012, and as a fellow of the American Institute of Chemical Engineers in 2014. So welcome, Professor Panagiotopoulos. Thank you so much, and please feel free to start your presentation.
Okay, thank you so much. I'm going to start sharing my screen, my PowerPoint. Here we are. And I would like to thank Fred and all of you for joining me in this seminar done remotely. But I must say, I will take a rain check for the invitation to visit Brazil, which I will very much like to do when conditions allow, hopefully in the not too distant future. So the work I'll be discussing today is work done over several years recently in my group. The work, of course, of very capable students and postdocs, specifically Hao Jiang, who was a postdoc in my group until 3 years ago, Jeffrey Yang, who just graduated. He's now at Nesta in Boulder, Colorado. Xion Yue, who is a current PhD student in my group, and Sina Hassanjani, who joined my group a few months ago as a postdoc. The support for the work has come from the Department of Energy and the National Science Foundation. So, what is it we're trying to determine, and why are these electrolyte solutions important? Well, they are important everywhere, but I will give just two examples that I provide to explain potential applications of the systems. This is a plot I took from a publication some years ago on fracking, on production of oil and gas through shale formations, and shows the flowback water salinity as a function of time after hydrofracture. And the curves are not important, but what is important is the realization that the concentration of salts ions in the flowback water is many times that of seawater. So we're talking about very concentrated electrolyte solutions for which thermodynamic descriptions are very difficult and typically only possible with empirical models over a very narrow range of process conditions for which data have been measured. And of course, the other great area where ions play a key role is biological systems. For example, and this is a free energy surface of a small lysopeptide we studied a few years back in my group, and it's not, the specifics are not important. What is important is to realize that ionic interactions mediated through ions in solution play a key role in biological function, recognition, reactivity. Everything in life depends on the transport and binding of ions and charged groups. So we would like to be able to describe these systems at the molecular level as accurately as we can. And this is the objective of the work that we have been doing. In doing that, one realizes fairly early on that some of the key macroscopic properties of the solutions are very well studied over many years because of the importance of these solutions, but have not been studied. So they have been studied experimentally and have been fitted to phenomenological correlations, but they have not really been routinely studied from a molecular simulation point of view using atomistic detailed models. Two specific properties that have that are the focus of my work and had really not been studied very extensively previously are the activity coefficients, which are, of course, describe the differences between a solution at a certain concentration and a reference state. In electrolyte solutions, that reference state is the infinite dilution state at 0 concentration, and I will use here my pointer. So 0 concentration here on this plot would, by definition, by construction, result in an activity coefficient gamma equals to 1, below gamma is 0, and then electrolyte solution non-idealities are described exactly at the limit of 0 concentration by the very well-known de Broglie limiting law, which was, by the way, a topic of a whole seminar in this atoms series a few weeks back by Professor Kondogiorgis. That red dashed line, when you plot log gamma versus the square root of the concentration, the slope of that depends only on the dielectric permittivity of the solution in which the electrolyte exists. So experimental data for electrolytes, for 1,1 electrolytes, typical, would go down following the limiting law at low concentrations, and then they start bending upwards, meaning that the interactions become less favorable. And this happens because of the fact that the ions start crowding around each other, they have size, and they also change the solution structure in a way that makes this interaction less favorable than they are at low concentrations. The other property that's well studied but hard to simulate is the solubility of the salt in solution, which is shown in this plot by this vertical line representing the solubility. So above the solubility limit, in principle, an experimental solution will not exist. Crystals will precipitate out of solution. In simulations, this is a lot less clear what will happen, since nucleation and growth of crystals can be very slow if you don't have a seed of appropriate character. So we are going to try to do this for molecular models as well as we can. What are the challenges in the simulation methods? Well, I'll remind you of the definition of the activity coefficient log gamma here. This is defined by taking the chemical potential, free energy per mole of the solution, and expressing it as a sum of a reference state, which in this case will be the Henry's law, the infinite dilution reference state, the ideal term, so this combination is the ideal solution term, and this describes the non-idealities. So in order to get a simulation method to describe, to compute these activity coefficients, you need a method to get the chemical potential at a finite concentration, and you need a way to get the infinite dilution chemical potential. Many standard free energy calculation methods, such as Widom insertions, for example, do not work for dense aqueous systems and strong interactions. And the chemical potential at infinite dilution is not a simple quantity to get. So how did we solve this? This didn't require tremendously original methods, but essentially it's a well-calibrated thermodynamic integration method that we can use to get the chemical potential at a finite concentration. So you have a solution which in simulations is in a small box, periodic boundary conditions, a few hundred or a few thousand water molecules. And in it, you have the salt, which is sodium and chloride, here schematically shown, already in solution. And then you're adding slowly an additional ion pair. And you do that, it turns out, by first blowing up the van der Waals radii of the ions, so that you do that in 10 steps. And then you charge up the ions. So Q equals 0 initially, and then you start putting charges on the ions, and you do thermodynamic integration to get the free energy change on introducing an additional ion pair in the solution. And the primary reason this has not been done before is that to do it with reasonable accuracy, with low statistical uncertainties, to get activity coefficients, you need very long simulations. So this, for a single point, a single concentration, to get reasonable statistics, you need almost a microsecond of simulation of time, of molecular dynamics, running time, in order to allow for the ions to sample all the relevant configurations and the water to relax properly and so on at the corresponding condition. By the way, I enjoy very much being interrupted. We have plenty of time for questions at the end. I was told to leave 20 minutes at the end, but we can start using that up during the talk. Well, I don't know how you would like to do that in terms of interrupting me. You can send a chat, and the people who are controlling the seminar can stop me and ask a question, or you can just unmute your microphone and ask a question. I'll be happy to do that. Okay. No
it's
question.
up to you.
Yes, Fred.
It's up to
Sorry, I missed the question.
No. It's up to you.
Oh, it's up to me. Yes, absolutely. Yes. So anytime you want, I'll pause at appropriate times to allow the audience to ask questions. So we solve the problem of getting the chemical potential at a fixed concentration, at a given concentration. How do we deal with the infinite dilution? One possibility is to slightly cheat, and I'm not really meaning that seriously, but we know that these solutions follow the Biológica limiting law at low concentrations. So we can take the measurement we have of the chemical potential at a relatively low concentration. This is square root 0.1, so square root equals to 0.1. So the actual value itself is only 0.01 moles per kilogram, molarity. This point here, this red point, we expect to follow the Biológica. Actually, if we want to be even more accurate, we expect there are some slightly, some empirical modifications of the Biológica that follow experimental data very well. So this continuous green line is experimental data for sodium chloride, and this dotted line is this equation, which is called the Davis equation, with the appropriate dielectric permittivity of water, and you can see that it follows experimental data very well. So we can anticipate that our chemical potential here at a finite concentration should be on the equivalent line with the permittivity of our model water, which is not 78, it's 73. So by having that placed on that line, it means we now know the reference chemical potential. In more recent work that Sina, my new postdoc, is doing, we're actually able to calculate that infinite dilution chemical potential directly, but that leads to slightly larger uncertainties throughout the calculation of gamma. And finally, the last thing we need to really worry about in these systems, if we want to get accurate calculations of activity coefficients, is finite size effects. I told you that these solutions, we have a few hundred or maybe a couple of thousand at most water molecules moving around and a few ions. At low concentrations, it's only a few ion pairs. It turns out that because you have electrostatic interactions, you do Ewald sums, you have an infinite array of periodic boxes, and there are strong, strong finite size effects. Jeffrey studied this extensively, and it shows on the left side a couple of typical results for the chemical potential as a function of concentration, as a function of box length, 1 over L, with three slightly different ways to do the boundary conditions for the Ewald summations at infinite dilution. So you can do it with conducting boundary conditions where the medium surrounding your infinite collection of cells has infinite dielectric permittivity. You can do it with the permittivity of the medium. You get slightly different results, or you can do it with grand canonical simulations. These are done with an implicit solvent system, and you can see that the differences, which appear to be quite high at low concentrations, this kind of differences will result in large shifts in the activity coefficient. At higher concentrations, you have more. All of these different methods are different at finite box size, but they all converge to some infinite system size value if you extrapolate properly. So you really need to do a lot of work to get these calculations properly done, equilibrated, and corrected for finite size effects. Of course, before you do all the methodology, you need to start with a molecular model. What is the molecular model? How do we describe water and the ions in solution? Well, there are many, many different water models. I took that from a table from this website. Many commonly used water models, and these are the acronyms, SPCE, SPC, TIP4P, so on and so forth, describe the water as a Lennard-Jones sphere with a certain epsilon and sigma, and a distribution of charges with a certain geometry. The differences between the models is the values of epsilon and sigma and the precise details of the geometry and the angles and so on and so forth. These models all fall in the category of fixed point charge water models with the Lennard-Jones description of the van der Waals interactions, of the repulsive interactions and the long-range van der Waals. And they contain most of the workhorse water models that we have. There are equivalent models for the ions, and where the interactions are dominated by the charge, which frequently is assigned to be, for strong electrolytes, positive 1 electron or negative 1 electron. So 1, and chloride has a charge of -1 in solution, and it has some parameters that are optimized with respect to some properties of the ions. Questions, comments? Okay, so we have the methods, we have the models, let's do the calculations and see what we get. So with the initial set of calculations we did some years ago now, resulted in the interesting observation that all of the reasonable model combinations with fixed point charges shown here, and many others we did. This is TIP4P, SPCE, JC means Young-Cheatham, SD is Smith-Dang, Tosi-Fiume, and so on and so forth, behave in a qualitatively similar way. At room temperature, they start, of course, at 0 by construction. They follow the limiting law reasonably well with the correct dielectric permittivity for the model water. But then they all deviate from experiments, which is this green line here, predicting higher non-idealities at high concentrations, except this particular model, which is a particularly bad model for water based on exponential 6 interactions that I did in the early 2000s, fitting the VLE properties of water. So this is not a good model. But the others are all reasonable, and they all deviate from experiments in a similar direction. And this is a typical uncertainty of our calculations. So this suggests that despite the great variety of properties and models, the calculation of the activity coefficient suffers from inaccuracies that all go in the same direction. So there must be something were missing. Okay? We'll see what that might be a little later. The other property I promised to study, the solubility, also shows systematic deviations from experimental data. And this is a typical, at room temperature, sodium chloride, 298. This is the experimentally measured solubility in molar units. And these are the results of the same set of models I was showing earlier in the previous slide for the activity coefficients. So some model combinations predict almost a factor of 60% or 70% lower solubility. Others, and it turns out that this is the best model for the activity coefficients, the SD, the Smith-Dank model, the blue triangles. That is the worst in terms of the solubility by a factor of 6. So it underpredicts the experiment. They really want to precipitate out of solutions. They don't want to be solvated. And that's a serious issue that has been seen in many biological simulations, that the association between ions seems to be stronger. And this is because the models used have a solubility that is much lower than the experimental solubility. My bad water model has a terrible solubility of a factor of 50 or so lower than the experiments. Incidentally, at the time we were publishing, these calculations, if you recall, are done with free energy calculations. So you measure the chemical potential of the salt in solution, and then you do a Frankel-Ladd integration in the crystal to calculate the chemical potential of the crystal, and you match them and you find what the solubility is. But there is an alternative for solubility calculations, right? Instead of doing this elaborate free energy path, you can just place a crystal in contact with solution and measure the equilibrium solubility, right? And this has been done many times, and the calculations, which need to be quite long, like multi-microsecond molecular dynamics interfacial calculations, gave values that are quite a bit off our calculated values, which had also been reproduced by other groups doing free energy calculation. So for a while, there was a big discrepancy. Why are the molecular dynamics interfacial calculations not matching our free energy calculations? And it turns out that there are very subtle effects in interfacial calculations having to do with the charge interfaces. So if you have a crystal, salt crystal, and solution, the interface of the salt is charged. I mean, it absorbs ions differently. Different ions are absorbed differently. You have these strong dipoles at the interface, and the dipoles see each other through the low dielectric crystal. So they raise the free energy of the crystal and result in effectively much higher solubility. So to get the right answer, you need the interfacial calculations to be done in a very large box with a very thick crystal slab. And this is what we showed in this paper, where we calculated the solubility with molecular dynamics with interfacial calculations and showed that it converges to the free energy value only for very thick slabs. So that's a side issue. The key message thus far is that basically all the fixed point charge models overpredict the activity coefficients at high concentrations and underpredict the solubility. So the ion-ion interactions are not as favorable at high concentrations as they should be. What is happening? What is missing in these models? Well, one obvious answer is polarizability. These fixed point charge models do not allow for distortion of the charge distribution in an electric field. And of course, ionic solutions have ions, which create strong electric fields, which should distort the electron distributions. There are now quite a few good polarizable models for water. Calvo and Cummings and Patrice Paricot came up with a Gaussian charge polarizable model, which was taken and refined by Baranay and Kiss. This is referred to as BK3. This is a good water model that reproduces the bulk properties. And they describe the interactions, the repulsive interactions with exponential 6 instead of Lennard-Jones. They have Gaussian charge distributions instead of point charges, and they have Drude oscillators, which means little charges connected to the spring to a central site to describe the polarizability. My own group, some years back, Hao Jiang, the postdoc, came up with a simplified version of this model, which we call HPP, hydrogen bond polarizable, which has fewer sites and can run faster. Will these models that include this very important physical characteristic of water do better for the properties we're interested in? Well, the first example we did with sodium chloride and water we were very excited. We were very happy because we didn't fit this experimental data curve, the line, and our points, which came from our BK3 calculations, matched the activity coefficients at room temperatures exactly. But it turns out that the temperature dependence is not right. So if you go to higher temperatures, 373, you start seeing deviations. This is the non-polarizable, polarizable, open circles, filled circles, open triangles, filled triangles, and at 473 Kelvin, the non-polarizable and polarizable models predict the same relatively poor activity coefficients at high concentrations. So the temperature dependence, even with the polarizability included, is not right. And the solubility is also not quite right. So the BK3 model, shows the way the calculation of the solubility is done with plotting the chemical potential as a function of concentration for the solution, and the dotted lines are for the crystal. And you see that the model predicts a solubility that's a factor of 6 too low. Again, the same direction. So we have come to the unfortunate conclusion that at least the current generation of water and ion models cannot really describe both solubility and polarizability and activity coefficients correctly. Now, there may be that the polarizable models have not been optimized long enough to be able to explore combinations of parameters that can capture these properties. And I think there are a couple of very recent papers that I saw that suggest that that may be the case. So it may be possible with a good polarizable model for water to have a good model for electrolyte solutions that captures all of these properties, but that remains to be seen. For the fixed point charge models, these have been optimized for so long that I am really confident to say that you cannot find a model combination, a parameter combination that will do well for all these properties and for the temperature dependence of these properties.
Tassios,
yes.
Can I jump in? Joachim Groß speaking.
Good to see you. Go on.
Hi. Tassios, how about the parameters in the model of the ions? Is that unambiguously known? Because you sort of speak about...
No, you're absolutely right. So neither, I think, my interpretation of this poor temperature dependence is that it's mostly a defect of the water model. But the ion models are also not clear that they are correct. It's not clear what the right value of the charge is. So as we will see a little later, the full charge models suffer in their description of transport properties of the solutions. And so it is a combination, of course, that we need to worry about, water and ion model. And I think there is blame to be apportioned in both categories, in both ions and water.
Thanks for your answer.
Thank you. Other questions? Okay, so one of the things that Yorgos Kontogiorgis actually and other people have thought about is perhaps, and this is an aside, this doesn't is not connected to the quantitative calculations of activity coefficients, but it asks the question: can we use these molecular calculations to say something about the contributions of the different ions to the non-idealities in solution? And there is a lot of experimental controversy, of course, for single ion activity coefficients and whether they're even meaningful and can be defined properly. But in simulations, we can actually define these very, very well. Namely, we have our solution of water with existing ion pairs, and then we slowly insert a single ion. Of course, strictly speaking, you cannot do that. You cannot have a non-neutral system. So when you're inserting a single ion, you're also inserting a uniform neutralizing background to keep the system neutral and enable the Ewald sum calculations, and measure the non-idealities in solution. And you do the same thing for, this is for sodium, this is the chloride, and lo and behold, if you add these contributions, you find that the non-idealities, the activity coefficients you calculate, exactly match what you calculated from your properly done pair insertion in solution. So methodologically, it's a clean definition of single ion activity coefficients in simulations. And you find quite interesting observations. This is very preliminary. We are still working on it. So don't take a snapshot of this and hold me to the actual values yet. But the sodium, of course, is these black triangles, and the chloride is these blue squares. And you find that they behave in a very different way. The sum of the two, which is this curve that you've seen before, is what is measured experimentally, but it turns out this is coming from highly unfavorable interactions of the sodium, which is smaller, so you would expect it fits, but because of the positive charge, it doesn't like the charges of the hydrogens which are sticking out. And the chloride, which is bigger, actually does like it, and it's favorable all the way to quite high concentrations. So we plan to see whether we can extend that and see whether we can get single ion activity coefficients for a whole range of different ions and what sense we make on the contributions of the different ions to non-idealities in solution. So let's close here the discussion of the activity coefficients and solubility, saying we have the computational methods which reveal that there are deficiencies in existing model of water and aqueous solutions, and we have quite open questions on the best strategies to get systematic improvement. One of these approaches that we are exploring is to connect to quantum mechanical, to ab initio calculations, because many of the effects we're missing have to do with charge transfer and the real character of the hydrogen bonding, which is not properly described by existing water models. So we'll see how that goes in some time when we have some answers. Now, I was going to talk about nucleation in the solutions, but what time do we end it, Fred? What time?
Well, we will have 1 hour, so we have more 40 minutes, but we want to include some questions, some.
Okay. So let me switch the order a little bit and see if I have time. I will describe this nucleation, but let me switch to the transport properties that I would like to cover, because I think it follows very naturally from this discussion we have here. So I will share my screen here. Zoom, share, PowerPoint. Okay. All right. So
maybe before we go to the transport and nucleation, this is Abbas about here. Hello. While you're looking at activity coefficient, why not start looking at the structure? Because you brought up also the interface. There are indications
so
that
the structure of the solutions.
Right, not only at solutions, but also in interface, because there are indications that the structures are extremely different if you're at the interface or in the bulk.
Yes, it's a very valid study to look at the structure of the interfaces and the structure of the bulk solutions. These tend to be harder to get good experimental measurements for them, and I think that the macroscopic properties that people use throughout in describing the solutions also need to be done correctly. So this has not been the focus of my work, but I agree that it's a very important consideration. What is the structure of the solutions and how does it change with concentration and how does it change at an interface? Yes.
Right, because again, if you look at interface and we wanted to bring interface,
right.
The problem
I should say that the behavior of fixed point charge models and polarizable models at interfaces is very different. And that is a very important consideration. You need to have a good model to get a good description of the interface structure.
Okay, thank you.
Okay, so let me talk a little bit about transport properties. So transport properties are also important macroscopic properties for which experimental measurements are widely available. For electrolyte solutions, many people who have done careful measurements have used this equation to describe the deviations, the differences between the viscosity of the solution eta relative to the viscosity of the pure water, eta 0, right? And of course, at 0 concentration of electrolyte, this is by definition 1. And then the first term describing differences between the electrolyte solution and pure water, you have a coefficient A, which is related to ion-ion interactions and the same terms that result in the activity coefficient non-idealities in the biochemical theory. It's not the same coefficient, but it's related to that. And then this next term, the B coefficient, is related to the ion-water interactions. Now, for the B coefficient is very important in classifying ions in the Hofmeister series. So positive B coefficients are cosmotropes, which means that the viscosity increases, the water becomes more structured, whereas negative B coefficients are for ions that are chaotropes. The viscosity decreases and the water becomes less structured. And the question we were asking, and this is the work by Xuan, who I believe is in the audience, hi Xuan, is can we use simulations to get these coefficients and to understand how the different models perform with respect to these coefficients. And the way we would do that is we do a little mathematical manipulation to get a term on the left that depends on the measured viscosity, the measured concentration, and then this gives you a straight line if you plot it with square root of m with intercept A and slope B. Now, the B coefficients had not been measured, had not been calculated previously for realistic atomistic models of water and electrolyte, and I can show you why. If you do a series of measurements, a series of simulations at given concentrations, because the viscosity is a transport property, you get that in equilibrium simulation through a complicated formula with the stress tensors integrated over time, and that gives noise. So even though the individual simulations are all done at the same conditions and are quite long, you have a lot of scatter in the data. So you need a lot of statistical analysis, and we did that very thoroughly to get a good value for this coefficient by doing a bootstrapping analysis, 100 independent linear regressions, and simulations totaling many, many microseconds of simulation time. And if you do all of that, eventually you're able to get this type of behavior where the term on the left side here gives you the A coefficient we cannot really get very accurately. It has quite a bit of uncertainty. But the B coefficient, the slope, we get quite well from the simulation data, provided you're willing to spend a lot of effort doing it. So now, how does it work? How do our models perform? And we tried different classes of models. We tried fixed point charge models, very similar to the ones I was describing earlier for the activity coefficients and solubilities. So these are non-polarizable. We tried some models which do not do so well for the solubilities, but as you will see, do much better for the transport properties, and these are so-called scaled charge models. These are the Madrid model that Carlos Vega and his co-workers have been proposing, and they are used in this particular case in combination with the TIP4P 2005 water model. And then we tried these polarizable models that I already said capture some of the physics for real water systems. So how do they do? Well, this shows you that for sodium chloride solutions, we find that practically all of these classes of models follow similar behavior. So the non-polarizable models shown here clearly overpredict the effect of the electrolyte on the solution viscosity. So this is the experimental line, and the simulations show that the non-polarizable models are all too high in the B coefficient. The scale charge models do a lot better, and the polarizable models also do a lot better than the non-polarizable models, although none of them are perfect. Again, the amount of time is half a microsecond per point to get this done. This was published in Molecular Physics last year. If you try different salt combinations, not just sodium chloride, but different salts to try to understand what the B coefficients are for the individual ions, Hofmeister series, cosmotropes, and chaeotropes, you find that the same behavior that we saw for sodium chloride carries over to basically all the salts we tried. Potassium, sodium iodide, potassium bromide, and so on, all overpredict the B coefficients quite significantly. If you go to different, so if you decompose, that is the way that this is done experimentally, if you decompose the contributions of the individual ions, you find that the B coefficients contributions for different cations and different anions are shown here for the SPC and JC model combination, and you can see visually that for all the ions, these coefficients are too high when you use a fixed point charge model. This is, by the way, coming back to Joachim's question, this B coefficient, remember, probes ion-water interactions. So it does not depend on the water structure. This is all very low concentrations, and the structure is not changing as you add salt, but it does probe the ion-water model. And so there are problems in that I think have to do with in this particular case, with the lack of tolerability and also the lack of charge transfer interactions. You do the same thing now for the water diffusion versus salt. This is another property that's very important, and you find that the diffusivity of water for this particular model, well, the pure water, the model overpredicts the diffusivity of real water by a little bit. But more concerningly, the dependence on added salt is incorrect. So as you add salt, you have a much stronger reduction in the diffusion coefficient of water, which you could well imagine is related to the overprediction of the viscosity of the solution as a function of concentration. Now, one argument that people may bring up is, well, could this be a density effect? So could it be that these models don't predict the density of solution as a function of concentration? And the answer is no, it's not a density effect. The solution densities are all very well described as a function of concentration with these simple models, partly because... Come again? Come again? Yes, please. There is a question that I didn't hear.
May I have a question now?
Yes, please.
Yeah, so you said the density maybe is not the issue, but what's the dependence of the dielectric constant with the molality of the salt? Do you think this can have an impact on the transport properties?
So I did not study that. We are at relatively low concentrations. So I can't, I haven't really done that. The dielectric constant, the permittivity of pure water is a little off with all these models, but I'm sure that the dependence of the permittivity on salt concentration will also be incorrect. I have absolutely no reason to believe that that is correctly described by the classes of models we have. Okay, so now I got my transport properties. Let me go back then to talk a little bit about nucleation, if Fred will allow me to have another 10 minutes.
Sure.
Okay, so the question we're asking now is, okay, so we've talked about chemical potentials, activity coefficients, and solubilities, and we talked about transport properties. How about something even more interesting, which is the nucleation of salt crystals from solution? And for that, again, I think you will see quite clearly that it makes a huge difference what kind of model you use to describe the nucleation. In terms of methodology, we used forward flux sampling, which is a method that has been around for a while. It has some very nice advantages. It describes the nucleation process by sampling at a series of milestones defined by some order parameter, in this particular case, the number of ions in a nucleus that's growing or shrinking. We launch a number of molecular dynamics calculations with different initialization velocities from every milestone, and we find what fraction of these simulations land on the next milestone. Some of them will go to the next milestone, some of them will go back, and the nucleation rate is calculated as the product of all these probabilities times the probability of going to the next milestone if you are at the previous milestone, this conditional probability, times the flux from the initial basin to the first milestone. Now, the advantage of that is that you don't need to know which structure you're going to form, and you don't need the real dynamics. You don't bias the real dynamics of the system, so you may get the actual nucleation pathways. The disadvantage of this method is that it's very expensive, and so it has been not so frequently used. And this is work that we did with Pablo de Benedetti and his group, following up on some earlier calculations by Pablo. So once again, for these calculations, there is a simpler or apparently simpler alternative. To calculate nucleation rate, you can seed the simulations, and this is not a bad approach, but it turns out to suffer from some disadvantages. You seed the solution with a crystal, and you see if the crystal grows or shrinks, and that you use classical nucleation theory to connect that to nucleation rates. And these calculations were actually initially done, these seeded simulations, by Zimmerman and Peters in 2015, and showed this number here using a non-polarizable model for water. Then we repeated these calculations with forward flux sampling, and we got this curve, which doesn't match the previous calculations. And for those of you who haven't noticed, this is a logarithmic scale with a huge span. So the difference between this point and this point is 10 orders of magnitude. the difference between this point and this point is 30 or 40 orders of magnitude. So we're talking about real differences. The experimental data also don't quite match the calculations. So the initial issue was, okay, so what is wrong with, why do we have this large discrepancy? It turns out that the seeded simulations need to be extremely careful in how the definition of what is crystal and what is solution is done, and depending on the choice of that coordination number for calculating it, it also suffers from not knowing, when these calculations were done originally, the solubility of this model of salt in water was not known. So by using the wrong value of the solubility, 5.1, they got a very different value for the nucleation rate because it enters as a in an exponential with a square, so you get very, very different.
I'll have a to lunch.
Yes? Is there a question? Okay, so after we did this and we fixed the methodology, what we found, and the key point here, is that the polarizable models, which is this MAH BK3 model, the black squares, do much better in matching experimental data than the non-polarizable model calculations we showed you earlier, and also the scaled charge model calculations here, which have the right solubility, turns out to be very poor in terms of predicting the nucleation rates. So for the nucleation rates, there is a huge advantage of the polarizable models, and this has to do with the correct description of the interfacial properties and the interfacial free energies. So that's good, that's nice to know. It predicts, quantitatively predicting nucleation rates is important, but what we found in doing these simulations is that we were also able to shed some insights on the microscopic mechanism of the nucleation and how that changes as you go to high supersaturations. That's because we have access to the chemical potential of the solution as a function of concentration. So this is the chemical potential measured from our free energy calculations as a function of the concentration. And you can see here it goes up normally, and then at some point it hits a maximum around 15 molar. There are a lot of thermodynamicists in the audience, so you know the answer. What is this point at which the derivative of the chemical potential of concentration goes to 0? What does it mean for the thermodynamic properties of the solution? It's the stability limit, right? D mu d concentration being 0. So we are seeing on the free energy plot that for this particular model combination, 15 moles per kilogram correspond to a limit of stability. So what the question we asked was, what is the microscopic signature of this loss of stability in the solution? And to do that, we looked at the free energy barrier for nucleation of the crystal, and nothing funny was happening with that. It was not going to 0 at 15 moles per kilogram. The size of the critical nucleus was not diverging as expected from nucleation at the limit of stability of the solution. So the loss of stability is not a loss of stability with respect to solution crystal phase separation. It is something different. And it turns out that this is also seen microscopically. If you look at below 15 moles per kilogram, you find a classic nucleation and growth mechanism for formation of crystals. Above, you also see a classic nucleation and growth, except that it is a bit faster because the concentration is higher. What is the difference? What is losing stability in solution? It turns out the way to determine that is to not look at the solution and crystals, but look at large, disordered, amorphous regions that are the ones that precipitate out of solutions. In other words, the spinodal decomposition, the phase separation in these highly concentrated salt solutions is to a phase that precipitates out of the solution that has a very open, big clusters and amorphous, not crystalline character. And then within those regions, at much later times, you form the formation of the crystals. And this can be seen also by looking at the largest crystalline cluster versus the largest disordered cluster, which below the limit of stability grows linearly, but at and above the limit of stability, it shows a very, very different behavior, indicating that you have a different mechanism. Instead of having one-step nucleation and growth mechanism, at high supersaturations, these solutions lose stability and result in nucleation with a two-step mechanism. So this is what I wanted to cover. Let me go to the end and give my overall summary and allow time for questions. Major deficiencies of current models. Nucleation rates are good for polarizable models, but not so good for non-polarizable. Of course, we only did one salt in one model. We don't have a general answer. We hope to get one. We see two-step nucleation mechanism above the limit of stability. And my take-home conclusion is that we need new ab initio derived charge transfer models, machine learning potentials to really get the description of these systems properly done. With that, I'd like to thank you very much, and I'll be happy to answer more questions.
Thank you very much, Janos.
Thank you. So regarding the questions, anyone can write on the chat and we can read if he doesn't want to speak or doesn't have a microphone, or you can speak. So first, Guilherme asked a comment a while ago. Would you like to get back to that now, Guilherme?
I think it was answered during the talk already.
Okay, perfect. So who wants to be the first in this after question session?
Can I ask a question? This is Alberto from...
Yes, of course. Alberto, go ahead.
So Thanos, thank you very much for the overview. Since last time I saw this, there has been a lot of progress. So very, very interesting.
Good to hear that.
Yeah, always interesting. So one of my students is looking at viscosity and diffusion, and she's actually in the call, so she can correct me if I say something not correct. And we find we are consistent with you when we are looking at sodium chloride. We got the lower diffusion coefficients from the simulations compared to the experiments, and vice versa, larger viscosities. But she has also looked at other salts that are more complex. We have not submitted for publication because it's in collaboration with the industry. We should be able to submit next week. But for some strange reason, for those more complicated salts, we actually have much better agreement with the experiments. They are acetate.
For what property?
Both
for the viscosity of the solution?
The viscosity and the diffusion coefficients of water.
That would be interesting. It's not what we see for these simple salts, right?
Yeah, so for the simple, we agree with you. There is this discrepancy. I think Olivera is correcting me now. But for the other ones, we seem to have a better agreement. And Olivera, do you want to add something?
Good agreement when the values are normalized.
Sorry, can you open your camera, please?
What do you mean normalized? Normalized with respect to what?
The just value of pure water.
Yeah, well, okay. I mean, this in a sense, this plot here I'm showing normalizes it with pure water, right?
Yeah.
Yeah.
Yes, yes. So scaled, yes. So
yeah.
better agree. Yeah.
So it starts at 0 deviation because you take the ratio.
Yeah.
I'll be interested to see the data. I mean, I don't see in principle why a complex ion would improve the situation here. But you know, you can't argue with data if it's there.
I will send it to you and see what your thoughts are when they gives us the okay. Thanks.
Okay, Caio Soares wrote a question in the chat. First of all, I'd like to thank you for a presentation. Your work on the formation of sodium chloride solids was an inspiration for my master's and now for my doctorate. So I would like to know your opinion. Are we currently able to identify crystalline forms in the simulations of molecular dynamics, or are we still far away for these simulations?
I'm not sure I completely understand the question. If you define an order parameter or a local order parameter, Q6 or some other crystallinity parameter, you can mark ions as being part or not being part of a crystal region. That is, whether that is useful or not depends on what you're looking at. And what we find in these simulations is that the original designation of just looking at just the crystalline regions didn't help us understand what is really happening in the solution. We had to look at these open disordered clusters defined with a different order parameter than crystallinity to really see what the solution does. So my answer is yes, I think we are able to get a lot of information by trying different order parameters and deciding which one works best for the properties we're looking at.
Want to complement these questions, how is the dependence of what you observe in this dynamic system with the size of the system? Because you have shown that
in the nucleation calculation?
Yeah, yes.
So in the nucleation calculations, we didn't really do we always worry about system size effect. We didn't do an extremely systematic study. I mean, these are relatively large systems, and in order to see nucleation and growth, the system size influences when you see nucleation and growth, clearly. It depends also, of course, very sensitively on the supersaturation. So we were not really looking at quantitative, but rather qualitative aspects of the mechanism of nucleation. In calculating nucleation rates, which was the previous set of results, we did not do a systematic study of the effect of our calculated forward flux sampling rates on system size, but I expect the effect to be small relative to the uncertainties of the simulation, of the calculations. These simulations have uncertainties of plus or minus factor of 10. Okay, easily. Because these are rates. We have not really done that because it's also so expensive that we cannot really do multiple system sizes so easily.
Sure, but my question is, you observe qualitatively that at high concentration or high saturation, you may form a liquid-like phase before crystal.
Yes.
But at the same time, with very high concentration, we may form big structures that may be this structure, the stability of this structure may depend on the size of the box.
These are system spanning, almost system spanning structures. This should not depend sensitively on the box size. What forms at high enough supersaturation? You may have that in a bigger box, you will observe slightly different things at slightly different concentrations, but I don't think qualitatively it'll be different in a bigger box.
Okay, thanks.
Thank you, Fred.
I have a question, can I ask?
Yeah, go on, Professor Raja.
Can you open, Raja, can you open your camera, please?
Oh, open my camera. Hello.
Hello.
Can you see me?
Good to see you.
Good to see you. About the interdispersion of acids and bases, can you lump them instead of considering like an ion say HCl and sodium hydroxide in water?
The models we're using thus far are not able to dissociate water, do not have acid-base equilibrium built into them. The newer models with machine learning, we may be able to get models that can dissociate water. So the water models we're using have pH infinity, 0. What will that be? pH infinity, right? So it's a negative.
There's another question, the same line, two other questions, same things. If you have buffer, what happens? Or if you have a simple acid like formic acid, is it possible to simulate it at all?
Not with these models we're using here. You'll need to have models that will allow for dissociation, association and dissociation that these don't. Now, there are specific.
There is no problem of chemical reaction, right? Chemical equilibrium.
If you have some aspects, so dynamic reaction, you cannot cover with these models. You can say some things about the equilibrium constants and the way these free energies are influenced in different environments. So you may be able to say something useful about acid-base or buffer equilibria using these models. But before we get to that, I think we need to make sure that the models we're using are accurate.
Okay. The other question is, can you make some comments about chain formation, for example, in your iron-water interactions? Is really, maybe in dilute solution, this square root of m makes a difference. In higher concentration, it looks like it's more like proportional to concentration, like the viscosity or something. The A term has no influence whatsoever.
The square root of m term is not as important at higher concentrations. Yes, you're right.
So it'd be simpler to not think them of as a ionic, simple ion. No, I was just wondering. Going back to hundreds of years, Gopal or something, 1905.
Right.
Before the Bayakal. We can go back to that type of model simply.
That's right.
They consider proportional to concentration activity, for example.
Yes, at high concentrations, you can make some approximations that are not valid at lower. Yeah.
And the chain formation, anything about, the people talk about hydrogen, you have to have 12 chain in ionization potential or n number of hydrogens together.
We didn't really look at it, but of course you can analyze these simulations to get chain formation or to understand the structural properties of the solution. But this was not the focus of what we did.
Oh, okay. Thank you very much then. It's very interesting talk.
So next we have a question from Georgios, Professor Georgios Conto-Georges. Do you have your microphone, Professor?
Yes. Hi, Thanos.
Georgie, good to see you.
Nice to see you. Thanks for the talk. My question was about the dielectric constant, the relative permittivity from the simulation. It is an output, I guess. Do you calculate it from the various models?
I did not calculate it for many of these models, but it's entirely possible to do the calculation.
Do you have any idea if it is very different from model to model, from the different water models, or it is the same trend?
The good models will be comparable. So if you look here, TIP4P, SPCE will have comparable slopes here.
Also at higher concentrations?
I have seen very little work in proper calculations of dielectric permittivity at high concentrations of electrolytes.
You mean with the simulation, you mean data that are?
With simulations, correct.
Yeah, okay.
So
yes.
This is something that we would very much like to do, and this is part of what we hope.
Yeah.
But by the way, we have a nice project with Professor Conto-Georges, and we hope to start getting lots of results from that as well.
So that would be nice to see, Thanos. Thanks for the talk. That was my question.
Thank you. Yes, it's a good question. I don't have the answer.
We have also a question from Professor Joachim Gross. Do you have your microphone, Professor?
I have my microphone on. Thanos, my question is about the charge transfer. you speculate or conclude that
Yeah.
probably we need to extend our ion models to account for charge transfer.
Correct.
Do you expect we can get away with scaled down charges, or do you have to account for the statistics of it?
So the brief answer is, I think we'll have to do the hard work of getting models that properly describe the dynamic charge transfer that takes place in the solutions. Simply scaling the charges will not work, and I know it will not work it will work for something, so it will get the transport properties in agreement with the experiment, but it doesn't get all sorts of other stuff correct. So scaling will not be the solution.
Wow.
Doing something different will be. I don't know what that is. We have an effort currently in the group to try to look at these machine learning models, learn from ab initio MD, where all of this happens naturally, charge transfer, polarizability, everything else is there. That is impractical for the calculations I'm describing now. You cannot go to microseconds with ab initio MD. But maybe a machine learning model based on ab initio MD will be able to get that. And that's what we are pursuing.
Yeah. I have a second very technical question. Is there a good way of defining a van der Waals type of energy parameter for these ions? Is there sort of an infinite, whatever, dilution free energy that you can simply use and determine?
The brief answer is I don't know. I don't know that there is a good way. People have determined van der Waals parameters for ions using different metrics, using different fitting properties. I don't know what would necessarily be the best way to get that.
Wonderful. Tell us. Thanks for your talk.
Thank you, Joachim.
We have a question from Rian de Fever. Do you have your microphone working?
Yes.
So
I had a question regarding the section on crystal nucleation. You mentioned that you're not able to observe the stability limit by just looking at the crystalline clusters, but you had to identify these open disordered regions that occurred there. So do you think this is a general principle in crystal nucleation that's going to be observed in other systems?
Yes.
I'm thinking of like hydrates.
Yes. So my sense is that, and this has been seen by others, both there are suggestions in, say, experimental nucleation of especially multivalent salts, calcium chloride and so on has been seen. But my sense is that the reason you are forced to go to a two-step process is that this mechanism, the classic spinodal decomposition mechanism, would assume phases of sort of similar symmetry. So you go from a fluid, from a liquid, to an amorphous open clusters that look liquid-like, but not dynamically. They're arrested, they're amorphous. The crystal has a different symmetry. So whenever you have nucleation of crystals from solution, when you lose stability, you will have a two-step nucleation process. So I think this is a very general mechanism. I do not have proof for that, but my sense is that that's the case, yes.
okay. So no further questions in the chat. Does anyone have another? Professor Alberto is saying goodbye.
All right, so I'll thank everyone for participating in this. I must say, I was a little skeptical some time ago when you invited me whether this will work and how many people will be interested. But I was delighted to see that there is a huge number of people. My worry is that this will now work so well that we will stop having real seminars and we will have everything by Zoom, even when COVID is gone away.
I think it was very nice talk, and I think people appreciate this.
Good. Thank you. Thank you so much.
So now it's time to announce the next talk. Thank you, Thanos.
Okay. Thank you, Thanos. Let us all thank Professor Thanos.